Okay, and as you can tell, this chapter is called thermochemistry, which is just looking at, you can see this chemical reaction, is looking at the heat involved with all chemical reactions. I think almost everybody has to take Chem 162, and there's a chapter called thermodynamics, which obviously has a pretty similar name. And this is sort of the intro to that, and then we'll expand on it in Chem 162 in that chapter. There's a few majors that don't need Chem 162 versus 161. So this is sort of the shorter version, the intro half of the chapter. And then some of the stuff covered in that chapter, you need a few other chapters of material. So, okay, so these books are not really designed for people living in Hawaii in the tropics. So change heating your home to cooling your home, and then all the concepts, make more sense. In general, most of the electricity and energy on Earth comes from some kind of fossil fuel, wherever you are, whether it's petroleum or natural gas or even coal. Okay, so how much fuel you need depends on a couple different things, right? So you're heating your home, so how much heat you need is directly related to how much, the fuel you need. So how much is used, it depends on how much you need to use, which depends on the volume of the house, which depends on how much heat you lose through the cracks in the windows, etc. And again, flip it around for air conditioning here. The efficiency of the different processes, depending on what your fuel is, whether it's solid, liquid, gas. Then there's a few other factors as well. All right, so again, what we've been doing, right, is thinking about things on the atomic level. So we're going to jump in here and kind of macro level. You're talking about heating, and especially if you've lived anywhere that has an electric or a gas bill, you've actually paid for this yourself. All right, so we're looking at the umbrella term of energy, and that's anything that can do work. What's work? They're equal to each other. So again, we'll see this in Chem 162, the full picture, the entire energy. We're going to look at directly the heat that's coming up. And the generic, more Newtonian physics sense, work is where you have some force by a distance. And this kind of makes sense if you think about pushing an object. If you're moving a couch, right, you're doing work by you apply the force, and how far you push the couch, let's say in your house or something. It takes more work to move it a longer distance. So now as we get down to the micro level, the atomic level, then we're going to start getting down to the chemistry side of it and seeing the atoms and think to the collisions of atoms hitting one another. Okay, so let's stick in the Newtonian sense. There's two different types of energy. There's kinetic and potential. So kinetic energy is things in motion, and billiards we'll see off and on is a good analogy. Right, so here, when you shoot pool, you have the cue ball, you hit it, and then that energy gets converted, right? There's a collision, and the energy from the white cue ball goes on to the other ball, right? And that the energy is in motion and it gets transferred. So another way of thinking about this is when you rub your hands together, and if you're cold and it warms up your hands, right? That kinetic energy then gets converted to thermal energy, the friction of your hands rubbing together. All right, potential energy. Everybody, if you've ever, ridden a skateboard or a bike or driven a car downhill, you've already experienced this, right? You test your brakes, make sure they work, right? And you know that something higher in energy, higher height has that potential energy due to gravity. So what we're eventually going to look at is this potential energy as it applies to the bonds in chemicals and the bond between two atoms. And this is doing it generically here, the potential energy. It's stored in an object, so that's generically phrased that way intentionally. You don't really see it too much in Hawaii, maybe a little bit in people's individual homes if you have like a solar water heater up on the roof. But as you drive across the mainland and especially the southern states, you'll see water towers where the water is, up above the town or the home, and then they use gravity to create the water pressure. Okay, laws of conservation of energy. So energy is never created nor destroyed. Here, this is the first law of thermodynamics, which again, you'll cover in a much later chapter in Chem 162 equivalent, or wherever second Chem freshman Chem you take. Can be transferred from objects from one to the other. We saw that, the billiards, the pool balls. And then what you see a lot more in your normal life at home is that it's transferred into different forms, right? So it generally comes to your house as electricity, but unless if you live somewhere that has gas, and then when it comes to your house as electricity, you can convert that into light when you turn on the lights, sound, when you turn on the stereo, moving a fan is blowing wind. Like there's different forms. Okay, and so this is just showing you some of the things that, we do where you can change that energy. So, this is one's a spring. If you ever had a catapult or a, shot put or catapult or slingshot as a kid, these are all that type of theory. Same thing with if you have something that's at the top of the stairs, right? A bucket of water, if you walk up and put it at the top of the stairs, flight of stairs, it's got energy. If you knock the bucket over, the water comes pouring down, right? So here, this is the spring, it's spring loaded, and then you let it go, and that potential energy that your body, this girl pushed and set in, then when you let go, you see in the kinetic energy shooting up. All right, so there's different types of energy. There's electrical, right? That's the flow of electrons. We covered that, barely skimmed up against the surface with oxidation states and charge. There's a whole chapter on that in Chem 162. Heat or thermal energy, and we'll talk about this here in this chapter, the heat that comes and goes with chemical reactions. Light, we'll look and talk a little bit about light in a coming chapter as it applies to chemical bonds. Nuclear energy, there's a chapter in the book, but kind of depends on who you take Chem 162 with, if it's covered in much detail. And then our R2 are really here, the heat, and then down here, the chemical, right? Potential energy in the attachment of the atoms or because of their position. It's basically the attachment, which means the chemical bonds. So, for example, right, gasoline, you go to the gas station because you're out, you want to drive your car, because the gasoline, the energy in the bonds gets converted into work and the car will drive. So the gasoline is like your bucket of water at the top of a flight of stairs. And then what comes out the tailpipe of your car is the equivalent of if you knocked over that bucket of water and it bounced and dribbled and drained and went all the way down the stairs to the bottom stair. That's the carbon dioxide and water that comes out the tailpipe of your car. Okay, these units, I'm just covering it in here so you know them. We're not going to use these units. This is more the physics. So we'll use a joule. That's a typical, calories and joules are typical chemistry units. And then you can see here, this is just the interconversion of them, which more people in food, nutrition, and or engineering physics, where you're going between these units. You can see here, right, a kilogram of mass at a speed of 1 meter per second, right? That sounds like a force and a speed, because a speed would cover a distance. So I won't be putting a problem where we interconvert between these two, but if you need it for any of the homework problems or worksheets, etc., here it is. But I don't personally, I don't put it on the test. I feel like this is more of a physics that you would get in that physics class. So we just overlap with it. These are our two most important units. And in general, in the chemistry world, we stick to calories, but depending on what field you go on to or classes you take next, they interconvert. So calorie tends to be, and joule are the two units used in chemistry, and it kind of depends on what side of the chemistry field you're in, and who you're with and what field, and it kind of like a Venn diagram bounces back and forth depending on what biochem, physics, etc., engineering. But these are just conversions, just like there's 24 hours in a day. Okay, so where these things come from and sort of the size. So the joule and the calorie are the most common ones. The calorie here with the capital C, that's the one that we put on food. So these, the lowercase calorie, the science one, it's a pretty small value. So energy required to raise the temperature of 1 gram of water by 1 degree. Now, 1 gram of water is a pretty small amount of water, right? And again, 1 degree to Celsius isn't too much. So these units are not really too big. Usually our chemical reactions reported on a per mole basis are in kilojoules, so 1,000 joules. Right, then the rest of the table just starts to put, energy, makes it more tangible. Like, let's just do this one, for example. Energy used to run 1 mile, right? 4.2 times 10 to the 5th, right? 10 to the 6th would be 1,000,000. So this is 420,000 joules. Hence why they're usually reported as kilojoules. All right, so in these chemical reactions, you're basically going to look at and categorize everything into one of two ways here, either the system or the surroundings. So the system is the thing you're interested or looking at, and notice it states it here rather generically. We're still kind of in the introduction here as though it could be a physics class. As the material or process we are studying that energy change. The surroundings is everything else, the entire universe except our system. And in here, our system is going to be the chemical reaction. So it names it rather generically here. But we'll see it's going to be reactants to products coming up. All right, the conversion of the energy requires that the total energy change in the system and surroundings must be 0. So that's just what the previous slides were going over, is that energy is transferred, it's not created or destroyed, so it's got to go somewhere, right? If you pull, let's say an ice cube is your system and you pull it out, it melts. And what's going on there is the energy around in the universe went into the ice cube, and that it absorbed the heat. Conversely, right, you take something, I don't know, a cookie out of the oven, you set it down, the heat, the energy radiates out from the cookie to the rest of the universe. Internal energy is the amount of kinetic and potential energy a system possesses. So it's total, essentially total energy. The change in internal energy of the system only depends on the amount of energy in the system and the beginning. So beginning and the end means final and initial, which means reactants, beginning, products, end. You may have seen this term before, depending on math or physics that you've had, a state function. So a state function is an entity that only depends on the initial and the final, beginning and the end, not the process by which it happens. So again, final is products and initial is reactants. So this is a good thing to just memorize. You'll see this all year long. And if you're a bio person in OChem, same thing. Energy of the products minus energy of the reactants tells you the energy of the reaction. Okay, and so the idea of the state function means is this analogy here to hiking. So this is some mountain that's 10,000 feet, and the elevation would be the state function here, right? So it's only your beginning spot, the bottom of the mountain, and the top, the 10,000. It doesn't matter which path you take, A or B, you still went up 10,000 feet, right? So whether you go this vertical one right up it, or you take the more gentle, switchbacking one here, this doesn't affect which route you take, right? So the state function is these things that it's in this instance just the altitude. And so with us, it's going to be the kilojoules of a reaction. It doesn't matter how we got there. And so how we get there would be, path A for the chemical reaction would be, a reactant goes from A to B, then B to C, then C to D, then D to E, whereas path B would be from A to E directly. Energy diagrams, you'll see these in bio classes after this. You'll still see this in OChem. This is the way that chemists show that basically that altitude, but in kilojoules for chemical reactions. So if your initial is lower than your final, then that means your reactants are lower in energy and it requires some kind of energy to reach the products, right? This is when you're at the bottom of a flight of stairs and you walk it up to the top of the flight of stairs, right? The difference is a positive value, right? The final resting point is higher. So the delta products minus reactants will be a positive. And then the converse. And so the takeaway here is the sign, right? And this, so the initial to final where it's positive is something like boiling an egg, right? So if you've ever boiled an egg, you have to have boiling water and the heat from the water goes into the egg and it changes it and doesn't go back. The converse of that is a campfire, right? So, or, the gasoline in your car, but a campfire, you're around it and see it more. So you take a log and light it on fire, right? And the heat comes off. And so the products are lower in energy and the heat comes off. So as far as your system is concerned, the energy is negative because it's leaving, right? Your initial is higher. So initial minus final or reactants minus products, it's gone to lower energy. And then here's this picture flow of this, right? So if negative sign here tells us is saying that we have some system and the energy left it and it went to the entire surrounding. So the blue would be your campfire. The yellow would be, you sitting around the campfire and you can feel the heat coming off, but it goes in all directions. And whatever the energy from the system is, it's equal and opposite to the energy of the surroundings. And the vice versa of this is true, right? So if you think about this in the other picture, like a flight of stairs, back one, you can here on top, it's if you walked a ball up to the top of the flight of stairs, and then now if you're at that top and you hit the ball and it goes bouncing on down to the bottom flight, right? And you can go back and forth, which is basically what a battery does. When your phone dies or is near dead, you plug it in and it pumps the electrons back in, and it's like a spring. It's spring loaded and ready to work until the battery's drained again. And that's sort of this picture. So say the surroundings is your electrical plug and you plug your phone in, and when it's sitting there, this is what's happening. The delta E now is electrons, but it's being pushed back into the system, and then the system is charged up or at the top of the flight of stairs and ready to be used and go back and give the energy back out. So equal and opposite. Okay, so that total energy is the combination of two things. It's the combination of heat and work. The Q and the W are not state functions, and their value depends on the process. That's a little kind of physics and engineering, and really the short and skinny for this is in the chemistry world, we really try to minimize this work, right? And we'll see this coming up, and the reason for that is in a chemical reaction, you're doing it in a lab and you care about the heat coming in or going out because a chemical plant is going to use it or something. And so essentially in the chemistry world here, we want this W to equal 0. And if that W is 0, then the delta E is just equal to the Q. Now the opposite, the other way around is quite exactly what engineers try to do. So if the chemical your reaction that you're talking about, let's say, is gasoline, you want it to do the most work possible, right? Whenever you're shopping for a car, you want the most miles per gallon possible. You want the most work to be done. You don't want to just put the gasoline in your car and use it to heat up the car. That doesn't do you any good. You want to go somewhere. So this is our full equation, but the split depending on what your interest is, right? In the chemistry world, we want the W to be 0. And in the engineering world, you want the W to be 100% if you can. The less amount of energy from the gasoline lost in heat, the more you can put and apply to the work. All right, again, so here's that full picture. And we have these two in action, right? And in the chemistry world, we eliminate the work if possible, and the engineers try to maximize it. And this is why your car has a radiator, is because it's impossible to get, when you have gasoline being used in your car, to convert all of that to work and not have some heat. And you don't want the car to overheat. So you have water that's constantly removing the heat, but they try to minimize that. All right, in a little more tangible sense, if you've ever played pool, right, you go and the white ball is a cue ball and you hit it, and here they're just putting values to it. So if you ever play like on a brand new table, the felt, the table is actually really nice. On older ones, it's all beat up, and you lose some of that energy in the form of friction. So this is saying, you hit the ball and it's got 5 joules of energy, right? And the ball doesn't keep moving forever. And it would if there wasn't any heat lost on the table. And if you've ever watched or played or you like ice hockey, the hockey puck has very little friction on the ice. So that's why when they hit the puck, it takes quite a bit longer for it to slow down versus when you play pool, the balls eventually stop moving. It doesn't last nearly as long. And then here they're just, arbitrarily, but they're putting some money, they're putting some amount set to this. So 5 kilojoules, you lose 3 in heat. That means the kinetic energy transferred is 2 joules at the collision. And then this isn't exactly true, right? Because when you've played pool before, unless it's a direct perfect hit, usually the cue ball isn't sitting still. It still has some motion, but this is just an example. All right, so heat is the exchange of thermal energy between the system and the surroundings. Again, if you've been around a campfire, the campfire is the system and you're the surroundings. It occurs when there's a temperature difference between the two, right? Things flow from higher temperature to lower temperature. So until they're both the same temperature, right? When you have a glass of water and you put in an ice cube, the ice melts, the water cools down, and they meet in the middle. And if you've ever made cookies or something in cooked in the kitchen, you take something out of the oven, it's higher in temperature, you use a pot holder, pan holder, whatever, so you don't burn yourself because the pot or the pan is hotter, and it will transfer that energy to your hand and do damage. So the key part of this is usually when something's hot, you already know this and think about it, but this is now the way you want to think about it as a amateur chemist in the thermodynamic sense, is that something isn't really cold. What it is it's lower in energy. So when you take an ice cube out of the freezer, let's say, it's not really cold. What it is all those water molecules in the ice cube are lower in energy. And sort of like the way water goes down a drain in a bathtub, that ice cube is a heat sink in the middle of the room. And so all of the heat is sinking and being sucked into that one spot until the ice cube completely melts and is the same temperature as the rest of the room. Right? Because just the opposite is true. If you take a cookie out of the oven, the cookie is hot, and that heat dissipates in every direction until the cookie reaches the same temperature as the room. All right, so here's our first equation in math, and we'll do several problems of these. You'll even use this same equation in Chem 162. This is called the MCAT equation. We'll see why in a minute. It'll expand this. This is called heat capacity. The units, joules, so it can be in Celsius or Kelvin. We'll see, it doesn't matter because those units are the same size. The degrees of each of those are the same size. So you can't use Fahrenheit, but you can use Celsius or Kelvin. And it doesn't matter which because it's a delta T. We're looking at the change in the temperature. And mostly we'll be doing water, but there are other substances. And so since the capacity of an object depends on its mass, it depends on how much water is there. So for example, right, if you're making top ramen for yourself, right, just one cup, a cup of noodles or whatever, you can put that in the microwave on for a minute or so. But if, let's say, you wanted to cook pasta for your, a family reunion, your entire family, you need a giant pot, and it's going to take a lot more water. Thus, it's going to take a lot more heat to get it up to that boil. So it depends on the size, and then it also depends on the object, right? So let's say sand versus water, especially here in Hawaii. You've all been at the beach, I would assume, at some point, and the sun is shining down on the water, the same as it is on the grass. But when you get out of the ocean and you go to the showers or your car, the sand can get really hot, right, and burn your feet and be uncomfortable. But the grass and the water don't. Right, so water has a really high heat capacity, and is why we use it for heat removal in radiators for cars and other engineering applications. So that on the last slide was the generic sense of the heat capacity. We're more interested in the specific heat capacity, which is just the amount of energy, same thing, to raise 1 gram of material by 1 degree. So that stayed the same. But this applies, and there's known values for lots of different objects. Right? And so over here on the right, we see several of these. So water happens to have a really high specific value. So if you look in here, here are some metals, right? Then ethanol is the alcohol that people drink, right? Sand, notice sand it's higher than a metal, but it's pretty low compared to water, let's say. And this is why metals can get so hot, right? We cook with pots and pans because these values are low and they get hot fast. So if you put a pot or a pan on the stove and you turn it on high, the pot or the pan gets hot much faster than a pot of water, right? The water has a value, let's say compared to iron, 0.4 versus 4.18. It's 10 times higher, which means it's going to take 10 times more of the energy to heat up the same amount of water as it would iron. And some of these other ones like lead, a lot of pots and pans are actually made out of lead. It's even lower, 0.1 versus, 0.4. All right, so the combination of these gets us to the specific heat equation. Q, remember, is energy, is heat, right? M is the mass, so how much heat you need depends on how much material you want to heat up. Specific heat is the identity of that thing. Is it water? Is it sand? Is it a metal? And then T is how much you're heating it up, right? So if you were just going to make some hot tea, it doesn't necessarily need to get to a boil. But if you're going to make a hard-boiled egg, you actually need the water to boil. So how much how many degrees the change is will influence how much heat is needed too. Okay, so here's our first example. Now you've seen from the previous exam what the problems on the tests are like compared to these samples, so these are good to look at. There will 100% be one of these on the test. So classic roadmap here. Let's go through and solve this one. All right. How much heat is absorbed by a copper penny with a mass of 3.1 grams, whose temperature rises from -8 to 37? All right, so we've got our two temperatures, so we can figure out the temperature change. We got the mass, and then it told us what it is. It's copper, so we got to go grab that from the table. We know that our MCAT equation is what gets us there, right? And now you can see, right, the little delta here makes it look like an A, so MCAT. That's where the MCAT comes from. And now it's just plug and chug, right? We've got three of the things that we need, and we're solving for the fourth. So first, our temperature, 37 and -8. This is where the final minus initial gets important. Your final was 37, right? Rises from -8 to 37. So T2 or TF is 37 minus, right? And then it's a negative, so yeah, it's really adding. This is a classic example. You don't want to miss the problem just because this silly mistake, right? If you subtract 8, then you put a 31 in here instead of 29 in here instead of 45, and you'll get the problem wrong. Again, it doesn't matter Kelvin or Celsius here because it's a change, so the unit actually isn't there. And then the off the table, the mass they gave us, now you're pretty straightforward. You're just multiplying all three, and then guessing at the value. You'd have to have a good feel for these and be pretty good at math to guess. Right, our units all cancel, and we're in whatever heat unit was in here. So, and mostly we'll be using joules, as we'll see coming up, that most chemical reactions are in kilojoules. The bio world tends to use calories a bit more, and then physics uses other units. They overlap a little bit with joules. And then this is our total energy. So it said absorbed, so it should be positive, right? That's how much energy went in, but it's still an absolute amount, right? The reverse process would have the same amount of energy, but it would be flowing out. So I'm not really trying to trick anybody with the sign. Like, it's obvious if the temperature's going up that the heat's going in, and vice versa. Okay, I don't put one of these on the test. This is the only slide that's in here about the work. So remember that the energy is equal to the heat and the work. And notice here, right, this is our classic internal combustion engine. It's not really an engineering class. It's not at all. It's a chemistry class. So we're just covering it here because it's part of the whole equation. But for the most part, and especially some of the instruments we'll see coming up, and for chemical reactions, if you don't have a product that's a gas, then there is no change in the volume. And some specific chemistry devices, they're called bond calorimeters. We'll see them coming up. It's a cylinder that is screwed tight and there's no change. So, right, anything multiplied by 0 is just 0. So in the chemistry world, this delta V will be a 0, the W goes to 0, and it's not there. For those that are engineers, more engineer mindset, or plan to major in engineering, that goal there is then to maximize this delta V and thus maximizing the W. And here's just another unit conversion, but again, I won't put one of these on the test. It's just covering it here. And then it shows you one sample problem. All right, if a balloon, we'll just cover it. I'm not putting this on the test, but we'll just cover it since it's in here. A balloon is inflated from 0.1 liters to 1.85 liters against an external pressure. It even mentioned it here, external pressure of 1 atmosphere, how much work is done. So it's not 100%, but it works pretty much ideal, right? A balloon is rubber and can expand. 1 atmosphere means at sea level. So basically it's saying, you took in a deep breath, there was a little bit of volume in the balloon, then you blew it up to this value. How much work did you do? So obviously this is our new equation. W is equal to minus P delta V. And when it's at 1 atmosphere, this is pretty easy. So the difference in the volume, and here both the numbers there's no negative number possible for the volume. So this one's almost impossible to mess up. And then they chose this nice, state in our units of atmospheres, and they did it at sea level where it's roughly 1. So when the pressure there, when you're just at sea level, then it really just comes to the volume change. All right, then last was just this conversion factor to get out of this sort of stranger energy unit of atmospheres, liters, and into joules. Again, I won't put one of these on the test, like this isn't our focus. And those are the only 2 slides you'll see this on. All right, so this just summarizes it, but really what we care about and what you'll do the rest of the semester and in Chem 162 is the heat. And we'll dive back into the heat in Chem 162 and see that it's a little more complex than shown here. So a good slide that just summarizes everything up to this point in the chapter. Okay, calorimetry is the way that these things are measured. So again, the chemistry world, when you've got let's say you formulated a new type of gasoline, you want to know how much energy you get out of it so that you can compare it to current gasoline and how useful it'll be. The total energy from your gasoline is equal to the heat and the work that it can do. So if we can design a process where there's no volume change, that delta V goes to 0, the W goes to 0, then the energy of our system or your gasoline is just equal to the heat. And then if you can measure the heat in your calorimeter, that is the heat of your system. And we use our equation that we just introduced here. This thing here is called a bomb calorimeter because usually these things are done via combustion, right? And combustion is essentially a bomb, but they put it in this metal container where no volume change can occur. And the modern day or the general chemistry simple way to do this is you just put it in a coffee cup, right? Again, if your chemical reaction isn't producing any gas molecules, there won't be any measurable volume change, which doesn't apply to the gasoline, but it does apply to real simple freshman chemistry experiments. Okay, so these things are, I used one in an upper division chemistry class, so you obviously won't have access to this uh, in your 161 lab, but this is the way they look. This is like, Chevron, Texaco, these big petroleum gasoline companies when they're formulating and coming up with different forms of gasoline. This is essentially what they do. So you have this sealed insulated container. You've got the water in here. And then they have another container in here where this is the bomb part where it's sealed together and there can be no volume change. The lid isn't going anywhere. It's sort of like, an extreme metal coffee cup with no exit. And then this ignition wire is like what you've seen in the cartoons when they blow up dynamite. You charge this with oxygen gas, no other gas is in there, and then some sample. So it's basically just a controlled bomb explosion, and everything in here gets completely combusted, reacted with oxygen. There's no volume change, so no work gets done. This is the opposite of the internal combustion engine. And then you watch the change in this thermometer of the water. So you don't push down on a lever like they do in the cartoons, but you hit the button that sends this electrical spark through here. Your sample is completely combusted via normal combustion, balanced reactions that we saw in the last exam and covered 2 chapters ago, right? Some chemical, usually the ones we did were carbon and hydrogen combined with oxygen. You get carbon dioxide and water off, and heat. So this is your campfire, gasoline, etc. And the heat that comes off of the reaction is going to be equal to the temperature change in the water. So they measure the exact amount of water in here, and then the temperature, and you can then correlate the energy, the heat, with no work being done from your sample to the water, right? It's equal between the two. Okay, so let's do one of these. There's 1.01 grams of some sugar. It's burned, combusted in the bomb calorimeter. The temperature of the water rises from here, this initial to this final. The specific heat for that calorimeter is this amount. It's 4.9 kilojoules. So we can find the energy that came from the sugar indirectly by measuring the water. All right, here's all the data and info they gave us. We want to find the heat in a per mole basis. Everything in the chemistry world is reported via per moles. We know that the heat that came off the calorimeter is directly related to the heat from the chemical reaction. So we want to go through and find the heat that the calorimeter went up, and we know that that heat came from the reaction. Then last, it wanted it on a per mole basis, so we'll take that heat that we find for the reaction and divide it by the total number of moles, which I think this is glucose, but I forget offhand. Okay, so one other piece of data we'll need is from previous chapters, right? Grams to moles, right? And we'll divide it by the moles to get the per mole basis. Our temperature change, so this is a pretty accurate thermometer, right? Final minus initial, it went up in temperature, right? So the heat came off. All combustion reactions give off heat, so we already know which way the heat's flowing. They gave us the specific heat for that calorimeter. The reason they already know this as a value is they set it up and you use the calorimeter on repeat, so you don't have to, it's not changing items, it's always the same calorimeter. All right, so this gives us the amount. This one was in kilojoules, right? So we're already in kilojoules, which is common for the reporting of heat. We know that they're equal to each other, so the heat that the calorimeter experienced came from the reaction. So you flip the sign, but we already know the sign of it inherently since it's a combustion reaction, right? And you've sat around a campfire before, you know that the heat's coming off. So this is one where the sign is inherently obvious. All right, it was 1 gram and it's 342 grams. So we're dividing by this pretty small number and we get a large number. And that's expected, right? The reason sugar gives you energy, and the reason campfires, you light a fire to stay warm, is there's a lot of energy that comes off these reactions, right? So this is much bigger than those other little values we saw before, introducing heat in general. Okay, so like I was mentioning, there's a longer, more in-depth chapter in Chem 162, and this is the beginning part of that. So heat is really referred to as enthalpy. These are the same words. So the heat of a reaction is also, and really from here on out, should be called the enthalpy of a reaction. You won't hear a chemist call it the heat, really. They'll say the enthalpy. It's a little bit more of a physics term, but keeping track of the heats of reactions is a little bit more on the physics side in the chemistry world. All right, so this is that state function. It's the energy of the reactants and the products. So just like the altitude in the mountain climbing example. So then the delta means the change. And the reaction at constant pressure, right? There's the V. Again, we were trying to minimize that and leave it out. So the heat is actually equal to the energy when this goes to 0. That's essentially the work. These two values are usually the same. And notice here, right, the difference is largest for reactions that produce or use large quantities of gas, which is a combustion reaction, right? Combustion reactions give off gases. So we'll go and expand and talk about the difference between delta E H and delta E in Chem 162. But for now, these two are basically equal to each other. All right. Which way the heat is flowing actually has a specific term. These two you just need to memorize. And there, as you can see here, endothermic and exothermic. So endothermic is when the heat has to go in. So again, that would be walking a ball or a bucket of water to the top of the flight of stairs. That's boiling an egg. You need the heat. It has to go into the egg. And exothermic is the opposite. That's where the heat's coming off. That's your combustion reaction. That's a campfire and cooking in the kitchen. The heat comes off. That's exothermic. So when the heat is released, the reactants are, gasoline, something that can burn, and the products are lower. So it's a minus sign for the system. And then endothermic, it's positive. So this you just need to memorize. Exothermic is minus, endothermic is positive. You'll need this in Chem 162. You'll need this in OChem, subtle small thing to memorize, but obviously important to know which way the heat is going. All right, so for these exothermic reactions, the temperature rises due to the release of the thermal energy. That energy comes from the conversion of some of the chemical potential energy, right? We're breaking the bonds in the reactants, and that's converting into kinetic energy in the form of that heat. During the course of the reaction, the old bonds are broken and new bonds get made, and the products have less less energy in the bonds, and thus that energy is then lower. And we saw that in those energy diagrams. And so the difference in those energies then gets released in the form of heat to the surroundings. This is just showing some fireworks going on. So endothermic and exothermic are opposites of each other. That's yin and yang. So then everything here is going to say the opposite, basically. Endothermic reaction, the temperature drops due to the absorption of the thermal energy. Required thermal energy comes from the surroundings. So again, I like the analogy or the example of a hard-boiled egg, right? You put an egg in a boiling pot of water, and it's the heat in the boiling water that goes into the egg. But again, here's the bonds, right? So the old bonds are broken, new bonds are made. The new bonds are higher in energy, right? The endothermic means you took the ball or the bucket of water at the bottom of a flight of stairs and walked it up to the top. So there's energy that has to come from the surroundings to then change the product chemicals and make them higher in potential energy, right? The top of the stairs. Okay, so all of this is building up to what you see here, right? The enthalpy change in a chemical reaction. What this means is an extensive property is that the more you have of, in this instance, the reactants, the more energy, right? So, whether it's a little propane tank, that's what this is, C3H8, or if it's a super tanker that's in the ocean, the amount of energy comes off is proportional to the amount. That's this extensive property. Something that's an intensive property is what we saw in the last exam, and we covered, like density or the molarity of a solution, right? So the density of a nail is the same as the density of an aircraft carrier if they're both made out of iron. Doesn't matter the size, that value stays the same. The extensive one, it grows with the size. All right, so in general, right, you would do the enthalpy by the number of moles of the reactants, and usually it's the thing of interest that you pay for, right? So here, for example, is propane and oxygen, but you go to the hardware store or the gas station to get the gas or the propane. You don't go to an oxygen store to buy oxygen, right? So in general, we're not really interested in the heat of combustion per mole of the O2. We're interested in the heat of the enthalpy of the reaction due to the thing that's rare that we're going to get, the gasoline, the propane, whatever the carbon hydrogen substance is. We want to know what that heat is, that enthalpy per 1 mole. And then that becomes a conversion factor. So just like there's 12 inches in a foot, there's 24 hours in a day. The heat into one of these chemical reactions is the heat per mole of that unique reactant. So for this one here, it's a minus sign, right? Because it's combustion. All combustion reactions are exothermic. The heat comes off, so it should have a negative sign, and you flip your conversion factor depending on what you need, right? So if you were given moles, then you want moles on the bottom. If you were given a value in your problem in joules, then you want joules on the bottom. So the conversion factor is flipped one way or the other. And the same is true here for each coefficient in front. Now, usually again, oxygen is in the atmosphere. It's free. You don't go to the oxygen store. So in general, you're not really concerned about it. But depending on which reactant or product you're interested in, the conversion stays the same. The number of moles and the coefficient in front of the chemical go to that same value of energy. Okay, there'll be one of these on the test for sure. So in this one, how much heat, that tells us we're looking for an answer in kilojoules, is evolved. That just means, at the end of the reaction. In the complete combustion, that's combining anything. In this instance, it's C3H8, which is propane, with oxygen gas of 13.2 kilograms of the C3H8. Okay, so we need to know what that heat value is. We want to get out of kilograms into grams. That's fine. We've done that conversion before. From the periodic table, we know how many grams there are per mole. That's fine. We did that, last exam a couple chapters ago. Here's our new thing, is when we have that known amount of the reactant, how much heat is it going to produce? Okay, so first get out of kilograms and into just grams, then out of grams and into moles, because our heat is always reported in a per mole basis. Now our moles cancel, and this was a large amount, right? 13.2 kilograms. So we were expecting a pretty large energy value. And then technically, the sign should be negative, right? So it's here because it's an exothermic, and it's saying how much heat evolved. That means came off. But I'm not going to be a super stickler here about the sign for these types of problems, right? It's a combustion reaction. You've all been around a campfire. We all know the heat is coming off. So I won't be trying to trick you with a plus or a minus sign here. By convention, it is important to have the minus sign here, but it's inherently obvious which way the heat is flowing. Okay, so that bomb calorimeter that we saw before is a very expensive piece of equipment. It's not what what gets used in, say, freshman chemistry exams, labs. And so also, if you don't have a chemical reaction that gives off gases, then there's no volume change, and it's not really needed to have that big, complicated, heavy metal bomb calorimeter. You can achieve the same type of information with just a coffee cup and a thermometer, basically. So the chemical reaction is going to be the heat that comes off whatever reaction you've got in play going on. And the sign is flipped, right? Because the heat's going from the reaction to the solution, and all it is water. So you just keep track of how much water's in there. We know the specific heat of water, and then your thermometer tells you the temperature difference. You got to keep track of how much water you put in, but then you'll know how much heat was generated in your coffee cup and that it came from the reaction. So we use our MCAT and then divide by the moles at the end, and that'll tell us our kilojoules per mole. All right, so there'll be one extremely similar to this on the exam. This one, all right, what's our delta H? We've got magnesium and it's combining with HCl. We're getting magnesium chloride. It's already balanced for us, a 1 to 2. It told us how much magnesium is there. That's where we're going to get the moles to divide by. 100 mils, that's our mass of the water. And then here's our temperature change. We go to that table to grab the specific heat because it's water. And how do you know it's water? AQ means aqueous, right? So this magnesium is solid. So you're just sprinkling it in, but everything else is in water. And then there is a gas that's being evolved, but this is a very small amount. And for us, right, we're using a coffee cup, so we can just ignore that. And there's then our temperature change. So we plug and chug our MCAT equation, and the heat that the solution, the water, changes by is going to be directly the heat from the reaction. All right, our temperature increased, so that means that the heat came off the reaction and heated up the water. So inherently, we already know the sign should be negative at the end. Then our last step is just to divide that heat by the number of moles. All right, they didn't explicitly mention it, but the density's 1, which means 100 mils is 100 grams. We'll need the moles at the end. So mass off the periodic table, right? That's last couple chapters, last exam. So here's the new part. We use our MCAT, right? 100 grams of water, specific heat of water, and then that temperature change, right? We went about 7 degrees up, 25.6 to 32.8. 7, so that's where the 7.2 came from. All of our units cancel. They rounded it off here, but 3 times 10 to the third joules. It's positive as measured, so since it came from the reaction, it should be negative. But another one where we inherently know that it's negative, right? If the temperature raised up, that means the reaction gave off the heat. So the last step there then is just to divide the two, right? And this one they left in joules per mole, but you could move it to kilojoules, just kind of depends. And that's only moving the decimal point over 3 spots. So that would, make it 4.6 times 10 to the 2 kilojoules. I'm not going to, you saw from the last exam and what I tell you here in the lecture, I'm not trying to trick somebody with kilojoules versus joule. Okay, so what good is this delta H of the reaction? On the simple chemical sense, it's just this value to a chemical reaction. But if you are a chemical engineer or you're calculating engineering wise, how much you'll need to cook food, or like think about a submarine or an aircraft carrier in the military, in the Navy, where you need to know you have enough fuel to get the boat, submarine across the ocean. And that means scaling things up for size. So again, the delta H is an extensive property, right? If you've had a barbecue before, if you're only cooking one steak, you only need a couple of coals. But if you're going to cook for, I don't know, the whole entire family at some huge family reunion, a wedding or something, and there's going to be hundreds of people, you're going to need a lot more charcoal. So same thing here. So here's our reaction that gives this much heat. If we bring twice as much, right, carbon solid as coal, if we bring twice as much coal, then we get twice as much heat. And this here is a good example, right? This is one of the reasons that we have a buildup of CO2 in the atmosphere that we saw, and briefly talked about in the last chapter, and we'll see more coming up, is the heat that you get off when you are around a campfire or barbecue food. It's very hard to take that CO2 that's in the air and shove it back in and get the coal and the oxygen out as products. And we'll cover the reverse of this, the logistics of it, right? You'd have to collect CO2 and it's a gas that's dispersed around. So this is a little hint foreshadowing at the next thermodynamic chapter in Chem 162. Let me check the time. I'm gonna stop here. This is usually there's been a few questions when we end, and then this kind of opens up several examples. And I don't think we quite have enough time. And these tend to be a touch confusing. So you can see a little bit of math and reactions, and it jumps into a few things. So I want to spend a little more time on that. So we'll end here basically this last MCAT. And again, slide 38, sort of note to yourself for studying. There'll be one really similar to this on the exam where you're calculating the kilojoules per mole of some reaction from the water in the reaction that it's thrown in. And depending on, you know, if you're taking 161 and what lab and who's designed it, you might do a really similar reaction in the lab. Okay, I clicked on the unmute. And so this is, you know, the usual time for questions, comments, thoughts, feelings, whatever it is. Lecture course material today here or anything in general, I'm happy to hang out and answer questions and talk about whatever.
The constant, the specific heat capacity, we're gonna be provided like the table, right?
Yeah,
Or
I
do we
mean,
just Google? Okay.
no, you saw, let me go back up to, yeah, you like if you take a look back, I know our first test, you know, we didn't have a lot of equations in there as much or whatever, but um anything that's a constant like this in a table, I don't expect you to have memorized, and I don't want you wasting your time during exam looking it up. So it'll be like this here, where I give you the value. It's from the table, but I don't expect you to look it up. So the problem would, you know, would describe it like last time, like you see up the title, but then I'll give you the constants. Occasionally in these examples embedded in the PowerPoint, they leave out the constant. They do it intentionally. They want you to go dig through the book and you know, think about it. And you know, it's not, these aren't meant to exactly mimic what you know, the content, yes, but you know, blindly, you know, sitting down and doing it, they're not exactly like that. So yeah, good question. I'll always give you these constants that you need. You'll be given all the information needed to solve every problem. Either the constant will be uh up at the top of the test, like with equations. You know, I even give you the equations.
Oh, uh, I have like more.
Yeah, go ahead, Nick.
Oh wait. Anyone else next? No? Okay, cool. Workflow of energy. I think it's one of the earlier slides. I just remember it saying workflow. Uh,
Energy flow.
yeah, that one. Or it might have been like one or two slides before. Trying to explain like the signs for it.
Oh, that maybe this, but probably.
Yeah.
So this is where I think the analogy of, like, you know, a slinky at the top of a flight of stairs, right? You have to put the energy in the slinky. Like if you push a slinky and it goes, you know, bing bong bong all the way down, it never magically goes back up to the top of the flight of stairs, right? So
Yeah.
if you want something to be higher in energy, you have to put it there, right? And then once it's there, it's sort of like a slingshot that's been stretched back. It's ready to go and do whatever you want to do with it, which is basically what a water tower is, right? You just turn a valve on the water tower and the water pressure is there because of gravity. So in the chemical world, gravity doesn't matter. So what makes something higher in energy is the energy in the bonds. And it's a good question, and it should be a little slightly confusing now, but it won't be, I think, when we finish this chapter.
Yeah, I'm still so when you say energy, added, right? So if I have like, let's say a ball, and if I just go up a flight of stairs, I'm already adding potential energy because of the height difference, right?
Yeah.
That's pretty much like the change in energy is gonna be just the plus sign, and like if I wanna go negative, I just go downwards instead.
Yeah, so a ball at the bottom of the flight of stairs doesn't have as much energy as the one at the top.
Yeah,
And then to go from the one with higher in potential energy, you just flick the ball and then it's at the bottom of the flight, it's lower in energy. So the energy is being removed, it's being given off.
alright.
So that's the exothermic, right? You're around the campfire and the heat is leaving the chemical reaction and it's coming off and you feel it. You were part of the surroundings. But it's leaving. If you just think of the chemical reaction as the system, the energy is leaving the chemical reaction.
Okay, and on the equations for heat, MCT,
Yeah.
that Q's the heat. What's the actual units that we're gonna use? Because I saw like on the examples multiple different ones.
We're going to use joules. It introduced all the units just as an intro because people have different, it's a prereq and everybody's doing a different major. Some people are bio and they just, want to get it over with and probably never see any of these units again. And then some people are chem and they're going to continue to use the units. And then some people are, physics or engineering where they're going to care more about physics and engineering type of units. So
Yes, and
for us, we're
okay.
going to stick with joules.
So the heat, right? Heat's gonna be joules still.
Yeah.
Heat is joules. Yeah, because in one of the examples, or in all the examples, I saw joules and then like kilojoules and something else
So kilojoules is the same as joules. The kilo just changes the
to
size
a
of it.
thousand.
Yeah. Like time is when you describe how old you are, you don't tell somebody in seconds, you tell them in years, but it's still a unit of time, right?
Okay. Yeah, oh,
But
that's
or more kind of better is like when you tell someone how old you are, you just tell them in years. You don't tell them in kilo years because we don't live that long.
yeah. I
But
think it's because
if we lived thousands of years, you would say like, "Oh, I'm 2 kilo years old," but we don't live that long. So
okay. Mass is still grams,
yeah,
right?
yeah. So the units for this, like for this one here on the screen, it's always going to be this way, right? The Q is in joules, M is in grams, and so the specific heat. You actually,
Yes.
when you see the specific heat, it basically tells you the equation, right? You need to multiply the specific heat by some change in temperature that cancels the degrees, by some mass number that cancels the mass, the grams, and then you get joules out as the answer.
So we'll be using joules per gram. Is that a C?
Yeah, so right, the specific heat always comes as these units because it cancels the other units in the equation and just gives us the heat unit that we want left over. Right, the red lines are canceling and they
Okay.
don't cancel the joules, so that's a unit that you're left in.
Mhm. Temperature is gonna be on, are we gonna be using Celsius only or?
Well, so in here it's a delta T, and Celsius and Kelvin only differ by 100 degrees, by the number 100. But since we're subtracting two of them, it doesn't matter whether you use Celsius or Kelvin because the difference between the two is still the same. So, the boiling point difference in Celsius for water is freezing to boiling point is 0 and 100. And then in Kelvin, it's 273 and 373. So the difference is still 100.
Okay.
So it doesn't matter which you use because we're only doing the difference between them.
And heat flow, uh, I saw kilojoules per mole. I- was that only for like a specific?
That's for when it's a chemical reaction. So this one, like this example here is just doing, how much energy this piece of copper, this penny changed by, which we'll have one of these on the test. This is the intro part of it, but it's not an engineering class where, you're heating up, like how hot a bridge gets when the sun shines on it all day long or something. That's more of an engineering physics problem. Like what we care about more is this type. This is the type of calculation you'll do in the chem lab. You'll have 100 grams of water and you throw in some acid and you throw a little magnesium in there. And then you got a thermometer and you see the temperature changed, and that's due to the heat of the reaction. And
That example, can you explain it to me more? Just, I got lost somewhere along the lines.
yeah, no worries. This is a prototypical type of lab where you go over and you get 100 grams of water, right? And it's acid, so it's a solution that's got HCl in there. You throw in magnesium. Here is sort of like
A metal?
yeah, it is, but it's ground up like dust. It's not metal like your car keys. So you can just sprinkle it in. This is a really small mass amount, so you just sprinkle it in like sugar, or like you would salt your food or something. You weigh it at a scale, and then add that in. You have a thermometer in there and it changes temperature. That temperature change is due to this chemical reaction. So we use the
Okay.
MCAT equation from before to figure out the heat that came off of the reaction. And then the heat that came off, we want to report in a normalized unit. So like when you're driving a car, you tell the normalized unit we use is miles per 1 hour, right? You could divide it by any time, right? So in physics classes and engineering, they do like meters per second. You could divide by any time, but what's on our speedometers that we all use so we can relate it to one another is miles in 1 hour per hour.
Okay.
And so in the chemistry world, the unit that we divide it by so that it makes sense and you can use it is not the grams, because that can vary. It's moles, 1 mole. So here we needed to change this gram amount to moles, and then when we divided these two, we get the per mole value.
Okay.
So this is like saying, like when you go to buy a car, you look at like, I don't know, let's say the top speed, a Ferrari can go 220 miles an hour or something. That's the equivalent here for this magnesium. This is your magnesium reaction, and its capabilities are 4.6 times 10 to the 5 joules per mole.
Alright, and did the density matter anywhere? Or was it just
It
because it
yeah,
was one?
it did. So like, when these things like sugar, for example, and HCl is heavier than water, so the density is probably not actually 1 gram per mil, but I bet it's really close. So with a lot of these things, we just ignore little differences because they'd only be like a 0.5% or a 1% change, and we don't have, a way to like, it's not worth doing the high math. We're just doing the concept of it. Like when you measure, like let's say your speedometer was broken and you're going to figure out the speed of your car and you drive it for 1 hour or something. You have to pick a starting point and an ending point, and you just, you call it the gas station and then MapQuest it or whatever. But you could get out a ruler and like measure every inch potentially, but that's overkill to the exactness. Especially, down here, you're going to round it off to 2 sig figs anyway. Right. And, the thermometer only has markings on it that go to, the 10th place here. So the density, you'd be given the density. It'd be clear and mentioned in the problem. Here, they do this sometimes where they don't quite put in every descriptive detail for it.
Okay. And can you play that, like how they did the solution?
So, sorry,
Yeah,
Sandy.
cause like On the solution part.
Oh, like the animation?
Yeah, just so I could. Okay, and then did that, and then. That's the equation.
Right,
So
so,
he converted
right,
to,
if the density's 1, then 100 mils is 100 grams.
wait, where'd you get the grams per milliliter?
That's the density right here.
Oh, that was just given then?
Yeah, yeah, yeah.
Okay. And then that's the weight that goes in the mass.
And then this is the moles, right? It gave us the grams of it. So you go to the periodic table and that's the mass of magnesium is 24.31. So the gram amount that we used, so the whole point of this is you don't need to use a whole mole of material. Right? You don't need to weigh out 24 grams. You can just do some small amount and then
Okay.
you'll still know it in this, like if you wanted to figure out the speed of a car, you don't actually have to drive for an hour, right? You could drive the car for 1 minute and then extrapolate that to a whole hour.
Alright.
So this is the same thing here. We don't need to use 1 mole. It's wasteful, right? And they do this in freshmen and in chemistry labs all the time. You don't have to use, like if you're just trying to figure out this amount, the heat per mole of it, you don't have to use a whole mole of material. It's just a waste because you're just going to pour this down the drain. So there's no reason to waste, 25 grams of it. You can just use a small amount, just enough to see a decent temperature change, and then calculate the amount. Right. So
Okay.
this gives us the mole amount that we actually used. And then again, it doesn't matter Celsius or Kelvin because it's the difference starting to ending point.
And
And
then you do,
then you plug all that into the MCAT and we find the number of the heat that came off.
oh, you just used it. I thought you used the, no, never mind. And then that's -3. Okay, it makes sense now. How do you really know when the suns is gonna be positive or negative? I just remember you saying if it's gonna be combustion, you're gonna lose it because it makes sense, like heat's going exiting.
Yeah. So the temperature went up, right?
Oh, God, I'm blind. All right then.
Yeah. It's a subtle thing, but like so a lower temperature to a higher temperature, so the heat came off.
Okay, will that naturally just be if the heat went up, it's just automatically negative somewhere, or like at the end,
Yeah,
it's
yeah.
just
If
gonna
the
be
if the
negative?
heat if the heat went up, that means it came off the reaction. So conventionally, the sign must be negative. But it's sort of the same. It's sort of like I'll make the analogy here. It's like when you go to the grocery store, you obviously know that it's going to be negative money for you to buy the groceries and positive money for the store, right?
Yeah.
So it's the kind of same thing here. Like when, if you were formulating a new gasoline, you obviously know that the gasoline is going to burn and get off the heat because that's what's going to make the car move. So the sign isn't like it's more important that you can do all the math and line all the numbers up and multiply everything right to get to the right value. I'm not looking to trick you into, you put a negative and it's positive and take off points, right? Because
Alright,
what's the point of it? You know the sign, but you can't figure anything else out, right?
okay.
Yeah.
Alright, that makes sense now. I think that's all the questions I got so far.
All right, cool.
Have a good one.
I'm seeing if there it is. All right, yeah, cool. I'll see you Wednesday then.